Hi everyone and welcome back. Now on the last episode we did talk about a bunch of network type protocols, and those are just that. Those are a bunch of protocols that help our networks work properly. But why do we need our networks? We're not just laying cables for the sake of those cables, right? We're laying those cables and installing those switches in order for us to be able to connect to those networks and transmit some data and run some sort of applications on top of that network infrastructure. So that's exactly what we'll be covering today. We're going to be talking about application protocols. Those are the applications that are running on top of our network. And I don't think anybody's going to be surprised if we start talking about the one protocol to rule them all, at least nowadays, which is HTTP, Hypertext Transfer Protocol. Now, this is a pretty old protocol, and just as the name says, well, hypertext refers to a type of text that includes links to other texts. So basically, the way the World Wide Web was designed, just a interconnected network of documents, all of them linking one another, that was basically what the HTTP protocol was designed for, simple web pages with links. Obviously, nowadays, this is not true anymore. Now, we're using the HTTP protocol to stream binary data, we're streaming video and audio data, we're playing games over HTTP, we're sending email, we're even administering remote devices. We can run a remote desktop protocol over HTTP. We can do a lot of stuff over HTTP. Now, you do have to keep in mind that even though the protocol itself has seen a couple of evolutions over time, it's still the same old protocol that was invented many years ago. Now, fortunately, it's still very flexible. This is why it allows us to run so many things nowadays on top of it. But at some point, we are going to be facing a couple of limitations that are native to the HTTP protocol. And of course, those limitations and some of those vulnerabilities as well are going to be inherited by all the applications that use HTTP nowadays. Now, as you probably know, it's a client-server protocol. That means that we have a client, which in most cases is going to be your web browser. It can be an application on your mobile phone, for example, which contacts a server that is hosted, well, somewhere in a data center. It might be in a cloud, it might be a web application running or hosted by some company in their own data center, right? So this communication here is always initiated by the client, and it's kind of request response communication. Now, the client says something to the server and then expects back a reply. So the client either sends something to the server, as in here, take this chunk of data, and then the server tells the client back, well, I'm content with that chunk of data. I have processed it and it was okay, or it wasn't okay. Or the client asks the server, give me this type of resource, well, located at this address right here, and then the server is going to come back with a reply saying, well, this is the resource, here we go, or you don't have access to that resource, or the resource doesn't exist, or I'm not able to serve that resource to you, or whatever type of response needs to be sent back. So it's a pretty simple architecture. We're going to see in a couple of seconds that it also doesn't store any kind of state. So it doesn't really have the concept of a continuous session. We could do this, right, using some additional technologies such as web cookies, for example, but HTTP in itself is a completely stateless protocol. Now, by its standard, HTTP is going to run over TCP ports 80 and 443. Normally, we're running over port 80 whenever we're running pure HTTP. That is the unencrypted form of HTTP, as you can probably expect, since it's an old protocol. It's a basic design, did not include any kind of security features, nor security functionality. It doesn't know any encryption, it doesn't help you protect your data in any way. That's up to you. Well, later on, HTTP was evolved with an S at the end. Then it became HTTPS. And by pure convention, HTTPS is running by default on port 443, TCP 443. Now, I say this is purely a convention. That is because there's nobody stopping you from running encrypted HTTP over port 80, let's say. Nobody stopping you from running HTTPS over port 1234, perhaps. It's completely up to you. Now, these conventions are somehow useful because there are just so many clients out there. Everybody has a browser, everybody has mobile devices, has laptops and desktops, and a lot of client applications that are using the HTTP protocol. And whenever you type a web address in your browser, right, if it has an HTTP in front of it, then the browser is going to assume that you're trying to connect on port 80. If it has an HTTPS in front of it, then the browser is going to assume that you're trying to connect on port 443. Now, of course, your applications might run on completely different ports, but that's the point where you actually have to specify that port as part of the URL itself, as part of the address that you're trying to access. Because otherwise, well, everybody knows HTTP is supposed to be 80, HTTPS is supposed to be 443, and if it's not, then you have to inform the browser about this. Now, the way the client interacts with the server is by referencing some sort of resource. Now, if the client, for example, requests a JPEG file, an image file from the server, it's going to tell the server, here, give me the JPEG file at this location. And that location is going to be a URL, Uniform Resource Locator. Just a fancy way of saying this is how you address resources pretty much everywhere in the World Wide Web. Now, it can also be something like, I want to upload a picture. Right? If I want to upload my profile picture, then I'm going to add a payload to my request that I'm sending to the server, but I'm also going to add a URL with it as well, because that image that I'm uploading to the server has to go somewhere where that web server expects me to send a web page. It might be a URL that says something like, example.com/user/profile/ I don't know, edit profile.php, something like that, right? So I do need to add a URL, even though my payload might be actually binary data or text data or whatever payload I need to send to that server. Now, HTML, in case you're wondering what's the connection between HTTP and HTML, well, the markup language, that's the language of the web pages that are being rendered by your browser, that is just one of the possible payloads that can be included in HTTP requests. All right, so there's no one-to-one correspondence or dependency between HTTP and HTML. It just happened that, well, initially HTTP was kind of designed to transport HTML, but we ended up using it for so much more. So we pretty much always in our communication have a URL. Optionally, we might have a payload, depending on whether we're sending something to the server or we're requesting something from the server back to us. And we also always have an HTTP header. Now, the HTTP header includes a lot of metadata, a lot of additional information about the communication that is currently happening. Now, some example data that could be included in this HTTP header could be, for example, a way to identify what kind of client I'm currently using to interact with the server. This is how some web applications are able to identify if you're using a Firefox browser or a Safari or a Chrome or Edge browser. That's because all the requests generated by that browser include a small bit of information right there in the HTTP header in their requests saying that I am this type of browser, this type of version, and reporting that to the server. Now, this is just one example. The actual list of HTTP header possible values is huge. You can also define your own values if the server understands what you're trying to say in there. But just to keep things simple here, the HTTP header is also used to perform authentication. So whenever you need to provide some authentication information to your request, you need to prove who you are. Well, that information is also going to be sent along with the rest of the data in the HTTP header. And also the HTTP header is the one that specifies what type of payload am I sending to you, or what type of payload am I expecting from you. Now, that's because, well, I might be sending text, the server might be responding to me with binary data. I need to know this, because whenever I receive that response back from the server, I need to know how to interpret that bunch of bytes that I'm actually receiving in there. Should I read it as an ASCII text? Should I read it as a zip file? Should I read it as a JPEG file? That type of information, kind of like a file extension if you wish, but it's a bit more complicated than that. That type of information is also attached to the HTTP header in both ways. All right, so the client announces to the server, here's the type of payload that I've attached to my request. And the server then comes back and says, here's the type of payload that I've attached to my response. Just for your general knowledge, here's an example of a HTTP request header. So for example, you can see that There's the URL right here. That's the operation that I'm currently using over the HTTP protocol. That's the GET operation. All right. That's the address that I'm requesting. That's the protocol version that I'm using. What's the host that I'm contacting? What type of browser am I using? What type of responses am I going to accept? So you have a couple of accept entries in here. So for example, this first line here says that I'm willing to accept any kind of response that includes pure text, including a HTML language, XHTML and XML as well, or just XML as a response. All right. I'm also saying here that the languages that I'm accepting in my response are English or US English, and also the encoding could also be gzip. So I am willing to accept zipped responses. And remember, we just said this a couple of minutes ago, HTTP doesn't store any state information, so it has no way of built-in functionality to connect one request with another request or to make them seem like they come from the same client, or to identify some sort of a continuous session, or to authenticate once and then consider the identity or generate some sort of a token for that user identity for all subsequent requests. It doesn't have anything built into it that can help us do this. Now we can achieve this this functionality by using cookies, web cookies, which should be attached to your requests and then recognized by the web server. But again, this is additional functionality on top of the HTTP protocol. And fortunately, more recently, in the last few years, HTTP 2 was introduced, which includes a bunch of additional functionality that people have figured out that we kind of need to evolve the HTTP protocol, and since nowadays we're using it for so many things. And one of them is the ability to bundle multiple requests together in some sort of a quote-unquote session. So it's kind of like a session management built into the HTTP protocol itself. Now, of course, the web browser needs to know about this. The web application needs to support this, and the application code needs to be able to actually track this type of communication and this type of session information for it to work. But we're getting there. It's not really so widely used nowadays, but the technology is available, and hopefully we'll get to see this more and more over the years. We briefly mentioned a couple of HTTP methods, which are nothing more than just simple types of messages that we're sending over HTTP. So at the very beginning of the header, if you remember from the last slide, the first string that you can see at the beginning of the header is the operation that we're attaching, the method that we're attaching to that request. So this is one way of telling the web server, this is what I intend to do before we get to the rest of the header, before we get to the payload. We're just announcing the type of operation that we intend to perform. Now, some of the most common operations here, probably the most common one is the GET operation. That is a simple request for a resource. Whenever you're typing a web address and you're pressing enter in your browser, that request in the background is actually being sent as a GET request because you are requesting the contents available at that web address, right? We also have POST, which is often used whenever you're sending data to the web application, whenever you're sending an email, when you're attaching a file, when you're uploading a profile picture. That's when a POST request is being generated. And that's a way to announce the server, here, take this type of data from me and make sure you know what to do with it. We also have some other less common methods such as PUT, which is very similar to POST, except that whenever we're thinking about some sort of a database behind that web server, well, PUT is more a type of operation that says insert something in this already existing data structure, where POST is more like saying, create this new data structure from scratch. The head method is a way to retrieve just the header of the response, and the delete operation, you can probably guess what that does. Of course, you need to have permissions, and the application needs to allow you to perform all these operations. They're not just available to anyone out there, or they shouldn't be. So the client builds a request, announces the type of method, adds a header, adds a payload, and the server responds. So the server is going to respond with a message, which is going to be a type of code indicating how the request was processed from the client. It's a way of saying, well, Did you agree with what I just sent to you? Well, tell me something. Was it okay? Did it match your expectations? Was the request valid? Was everything in order? So we have a couple of response codes here that we need to be able to interpret from the server this time. So we have a bunch of numerical codes that can be returned from the web server, and these fall into a number of categories. The first category is the 200-something error codes. This basically says that the operation was successful. You could go for more granular responses here. That is, you're going to get a simple 200 response if your GET request was valid. So whenever you're requesting, let's say, an HTML page, when the HTML page comes back to you, it's going to come back to you along with an HTTP 200 response code. A 201, for example, might be for a successful put operation, if you're adding something to an existing database or next to other entries in the web application. The response codes starting with 300, these are redirects. You either trying to access a web resource that doesn't exist anymore and the web application is designed to redirect you to a new address. Maybe the entire website doesn't exist anymore and you're going to be redirected to a completely new domain. Depending on the type of redirection, or if it's temporary, it's the entire site has moved. Depending on what exactly happened in the backend, you're going to get a specific 300 message. But all of them are referencing some type of redirection that the client should follow. The 400 error messages, and notice that we've started talking about error messages now. 400 means it's a client error. So it's a way for the server to tell you it's your fault. The most common 400 error that you've probably seen is the 404 error, which is a non-existing resource. So whenever you're trying to access something that it's not there and you get a 404, that's a response from the server telling you it's your fault for requesting a resource that doesn't exist. I know, it's a bit funny, but the 400 error codes are considered to be client errors. This is also where we find things such as insufficient permissions. You're trying to access something where you're not authorized to access, or you're providing a bad authentication set of credentials. Right, you're failing authentication, and 401 is a server's way of saying you have provided bad login credentials. And of course, it's not always me. Sometimes it's you, right? Or the other way around. We also have the 500 error codes, which are server errors, whenever something doesn't work well on the server side. This is where you find error codes that the server generates whenever it doesn't have sufficient resources to respond to you. It has such a high CPU or memory load that it simply cannot process your request, or just general server error. You don't know what happened. The server was not able to conduct that request and process it properly. So that's a server error. Probably there's not much you can do about these server errors. This is something that needs to be investigated on the server side from the server logs. And since we are talking about security here, of course, we need to protect that HTTP protocol somehow, because by default, it doesn't have any kind of protection built into it. No security whatsoever. So this is where we find the TLS implementation, Transport Layer Security. Now, TLS is sometimes called SSL. That's because initially, this protocol suite was called Secure Sockets Layer, and it was the de facto method for protecting HTTP communications. Now, it has been introduced by Netscape a long time ago. How long has it been since you heard about Netscape, right? And at some point, that point being SSL 3.0, that's when the name change happened as well, and it actually became TLS. So it's the same protocol, more or less, more like it belongs to the same protocol evolution, but nowadays we're talking about pure TLS. Sometimes you're going to see this as a functionality in the next generation firewalls, such as SSL decryption or SSL offloading, and that's simply because people have gotten so used to the SSL term, but it's still TLS nowadays all over the place. Now, the greatest thing about TLS is that this time it wasn't just designed to protect, clear text or HTML or HTTP traffic. It can protect basically anything. So you're going to see remote access VPN solutions nowadays that use, for VPN access, use the TLS protocol. because it can actually protect any kind of data. It works just like an encrypted tunnel, and once you've established that encrypted tunnel, you can send whatever you want over that tunnel. It's going to be automatically encrypted. There are many implementations that can be used with TLS. Now, in most cases, a certificate is going to be implemented on the server because just like with normal, let's say HTTPS communication over the internet, the target is for you to authenticate the server to make sure that you're connecting to the right server, right? Whenever you're connecting to HTTPS google.com, you're basically downloading the certificate from Google, you're validating its digital signature up to the CA chain, up to the root CAs, and then you can confidently say that whatever I'm sending to this entity from now on can be trusted because I trust the certificate that was presented to me by that server. So the server certificate is always required. The client certificate is not always required. Usually the client has other ways of authenticating itself, username and password, one-time passwords, biometrics, whatever they need to use, or even nothing. Right? Or even, like in most cases, the authentication becomes part of the application itself. It's not a type of authentication that happens at the HTTP or TLS level, but it's something that happens in the application code. Whenever you're logging into Netflix, for example, you have to make sure that you're not sending your credentials to somebody other than Netflix.com, the real Netflix, right? But Netflix doesn't really care who you are unless you actually provide your credentials. And whenever you provide your credentials, well, that's enough information. You don't really need to present a certificate for that. And TLS is actually a suite of protocols and ciphers. That is, well, it's easy to say, well, TLS encrypts and authenticates your connection. That's it. But how does it do it? Well, who handles the key exchange? What algorithms are used to encrypt the data? What algorithms are used to ensure the authenticity of the data or the integrity of the data? So you have a bunch of other protocols and a bunch of other algorithms hidden behind this TLS umbrella that actually make this magic happen. These encryption ciphers are being negotiated in the first exchange of TLS packets. So whenever you're initiating that TLS connection to a website, for example, on the internet, part of that initial exchange is I'm telling you what type of ciphers I support. You're telling me what type of ciphers you support. And let's find a common denominator and let's see what matches between our two abilities. And then we'll start using the best encryption cipher, the best hashing algorithm, the best whatever we have out of each category, as long as they're supported by both the client and the server. And part of the initial negotiation is the TLS version itself as well. Now, TLS over time has evolved. So TLS 1.0 and 1.1 are not considered secure anymore. Anything lower than 1.2 actually is not considered secure anymore. So as part of the initial negotiation, we should try to choose between the client and the server a version of TLS that is at least 1.2, at least nowadays. Now, there are situations where a web server is badly configured or just lazy configured, and the web admin or the server admin thought that, well, why would I just care about all these ciphers? Let me just allow them all just to make sure that nobody's going to call me about some error in authentication or cipher support that they might be receiving. So in an attempt to minimize the amount of support calls, some web admins enable all the legacy protocols as well, even though most of them are terribly insecure. So this is actually a type of attack that can happen against a web server, trying to force a web server to negotiate with you the lowest possible security protocols that it can handle, thus allowing you later on perhaps to much easily decrypt that traffic or influence it somehow. That's called a downgrade attack. The server is supposed to be configured to not allow the usage of unsafe protocols or unsafe deprecated versions of secure protocols, such as don't allow the server to negotiate anything less than TLS 1.2. Here's an example of negotiated cipher suit. You'll get to see this if you check the connection status, the security connection status, whenever you're connecting to the website over HTTPS. So for example, an example of negotiated cipher suit would be something such as TLS AES, that's Advanced Encryption Standard, using 128 bits as a key. and Galois counter mode. So that's one way of saying that we're using block encryption. We're using the Galois counter mode in order to avoid replay attacks, and the 128 bits, that's the length of the key, right, that we're using with AES. Now, the last section right here, the SHA-256, that's the hashing algorithm. We're most likely going to want to ensure integrity of the communication as well, not just to encrypt it, but we also want to make sure that the content of the communication hasn't been tampered with in transit. That's why we add a hashing algorithm there as well. That's SHA-256. Speaking of web applications, it's worth mentioning APIs as well. An API being an application programming interface. It's just an additional interface, usually exposed by web applications. It's an interface that is supposed to be used in a programmatic way. That is an interface that other applications might be using to communicate with that application, or it's an interface that you might be using in order to interact with the application in an automated manner, as in through a script or through another third-party software that you might have developed in-house that needs to talk to your application. So let's assume you've developed an application and you want to allow your users to upload their profile pictures in your web app. And you don't want to store those profile pictures in your own data center next to your web application. You want to store them in some cloud, let's say AWS. So in order for you to be able to integrate your application with some storage service inside AWS, you're going to need to use AWS API for your application to contact AWS through its API and then store and then retrieve, of course, those images from the selected storage entity. Now, APIs are relevant because most of them, especially REST APIs, they also use the HTTP protocol. So they're nothing more than just requests and responses traveling over HTTP, but those requests are not now being sent by your own browser, but by some other application, maybe by a script or maybe by a program that you've developed. Here's an example of an HTTP request for an API. You can see it looks exactly like any other type of HTTP request because, well, that's the HTTP protocol. It starts with an operation, like a post operation right there. Then we have an URL, which indicates a specific type of resource. In our case, this is a cloud storage interface for monitoring IoT data. So what we're doing here is we're selecting a specific API, selecting a specific stream right here, selecting a specific sensor, which is a temperature sensor, right? And we're basically sending something to this entry in this API. Most likely is going to be a new value for this sensor's temperature, right? Since it's a post operation right here at the beginning. Now, as part of the headers, well, it might include some sort of authentication information. It might include an API key, right? An API key is some sort of a password, basically, which allows only legitimate users to interact with that API. And we're also saying that we're accepting as a response back from the API anything that is encoded as JSON. So we expect to receive a JSON payload. And here's the response coming back from the API. So assuming that we did send a new update for the temperature of that sensor, what we're receiving now is the current state of that sensor, which indicates exactly its value. In our case, it's going to be a temperature of 24.1. And perhaps some additional information such as what category the sensor is part of, or which building it's installed into, or whatever type of information you deem relevant for that application to return. So you can see in this case, the response is not a nicely formatted HTML page with CSS and JavaScript in it and a lot of stuff in there, but it's more like a simple request response communication based on something that can be interpreted by automatic scripts or applications. Now, this JSON response here can be easily parsed by a different application, which might be a dashboard, let's say, which displays the evolution of this temperature value over time. And pretty much all the APIs out there are going to rely on some sort of API key. That is some sort of authentication information that is being attached to each and every request that's sent to that API, and that authenticates the request as coming from somebody who has the necessary credentials, the necessary level of authorization to interact with that API. Now, of course, the more API keys you have, the larger the attack surface you have as well. And also the more resources you expose through that API, this also increases your attack surface. So make sure whenever you're designing these APIs or whenever you're protecting these APIs, try to think for just a couple of minutes. Do I really need to expose all this functionality over the internet? Or should I just restrict it to just a couple of methods, maybe just a couple of payload types, just to lower the attack surface as much as possible? Well, application protocols that deal with file transfers need to be protected as well, because we need to protect our files, right? And starting with the most basic file transfer protocol out there, which is actually called File Transfer Protocol, FTP, right? It is running over ports 20 and 21, and it's completely clear text. Again, designed back when people weren't so concerned with security, and both the control channel and the data channel, by the way, that's why we have 2 ports in there, all that communication is sent over clear text. So if you're sending your username and password to authenticate, those are in clear text. If you're retrieving the very sensitive file over FTP, that's going to be in clear text as well. Not much you can do about it. You can run it over a separate network, you can run it over a VPN, but FTP is still going to be inherently insecure. Fortunately, we have 2 ways of securing FTP. Fortunately, we have 2 methods of securing FTP. That is by adding an S at the beginning of the FTP protocol or adding an S at the end of the FTP protocol. I'm just kidding, but that's actually how they're called. Now, the first one is SFTP, which stands for SSH FTP. As you can probably guess, it's about running FTP over an SSH tunnel, a secure shell tunnel, right? So it's going to run over the same port as SSH because the tunnel gets initiated first, and then the FTP protocol is being run over that already established tunnel. So SFTP is going to run over the same SSH port, which is TCP/22. Now, the second method, as I said, is by appending the S at the end of the FTP protocol, which makes it FTPS, and that is FTP over SSL. Just like HTTPS, which is HTTP over SSL, we also have FTP over SSL. So this time the tunnel is an SSL tunnel, and we have 2 methods of ensuring the security of the connection with FTPS. The first one is called explicit TLS or FTP-ES, FTP explicit SSL, right? Something like that. This one is a method that kind of upgrades an existing clear text connection. So we're expecting our clients to initiate a clear text connection on port 21, just like with regular FTP, but then we are upgrading that existing connection with a specific set of commands, those commands being auth TLS or prot, from protect this connection, which makes that connection from that moment on, initiates a key exchange and makes that connection protected, secures it. And it's called explicit TLS because we need to explicitly request the fact that we want to protect this FTP connection. Now, another variant of this is implicit TLS, which is the actual one that is called FTPS. And it's called implicit because we are starting the secure communication from the very beginning, which also means that we're not going to be using port TCP/21 anymore because that one expects clear text, right, connections. If we start by communicating in a secure manner from the very beginning, we have to use a different port because the application needs to know that, well, whatever comes on port 21, it's clear text. Whatever comes on port TCP 990, that's going to be a secured FTP connection, and it's going to be secured implicitly with TLS. Email, of course, is still relevant nowadays. Why not? The email protocol that we're using all over the internet is called SMTP, Simple Mail Transfer Protocol. It's based on just a list of servers that are being announced in MX records in DNS. That's how your computer, that's how your email provider knows how to send emails to anybody over the internet by extracting the DNS entries according to the domain that you're trying to reach, finding out what are the addresses for the mail exchange servers in there, and then sending the necessary SMTP communication on a TCP connection over port 25 to those hosts. Now, nobody's going to be surprised about this. Of course, there's no security. Again, a protocol designed a long time ago when security wasn't really that much of a focus. Now, fortunately, we also have methods for protecting SMTP nowadays, which are very similar to what we just saw with FTP in the previous slide. So we have SMTPS, which is secure SMTP. That's about securing SMTP over TLS, right? You see the S at the end of a protocol, that's most likely going to be that protocol over TLS. It's kind of similar to what we saw with FTP, kind of similar to what we saw with HTTP over TLS. And we also have two methods of performing this operation. With explicit TLS, again, we are starting on an unencrypted connection, and we upgrade that connection using a special command, which is called start TLS. Just like the name says, we're starting a communication over TLS from that moment on. So the connection is going to start on TCP port 21, but again, then it's going to get upgraded to run on port 587. So that's going to be explicit TLS. And implicit TLS, again, SMTP/S, it doesn't require an explicit command to upgrade it. It starts communicating in a secure manner from the very beginning, and also starts communicating directly over port 465, TCP port 465. For the POP3 protocol, the post office protocol, the clear text version, of course, is going to run over port 110, TCP port 110, but we also have the POP3S, secure POP3, which is running over TCP port 995. Remember these for the exam. I also have IMAP. Again, the second method for retrieving messages from the server. IMAP is a bit more feature-rich than POP3 nowadays. So with IMAP, by default, it runs over TCP port 143, but we also have IMAP Secure running over port TCP port 993. A bit easier to remember because it kind of looks like 443 over HTTPS, right? Now, having all these secure versions of email protocols that we just saw, it's good. But nobody can guarantee that everybody's going to be using secure protocols from one end to the other of an end-to-end communication. So simply because those protocols exist, it doesn't mean that everybody's going to be using them. So a better way would be, if you really want to protect your email messages, to ensure that type of encryption and authentication and integrity protection right within your email message, not just relying on some networking protocols along the way. So this is where SMIME comes into play. Secure multi-purpose internet mail extensions. It's kind of a very awkward way of just saying, well, secure email, but that's the official name for it. So the most important thing here is that SMIME was designed to both encrypt emails and digitally sign them. So it's not just encryption to avoid, interception and man-in-the-middle attacks. It's also about digital signatures in order to validate who sent that email message from the very beginning. Which means that the actual way in which SMIME works, it's not really easy to follow, but I'll do my best here to explain it as simple as possible. So if I want to send an email to you and I want that email to be completely secured, that is protected against eavesdropping, and also I need to make sure that you know for a fact that the email came from me, you have no doubt about it, this is what needs to happen. So first of all, I'm going to need a digital certificate, because that's the identity, or that's the proof of my identity. All right, I'm going to need to have a valid digital certificate that you can recognize and you can validate. You also need to understand SMIME, right? Your email client, in order to be able to validate my identity automatically and also to be able to decrypt the contents of that email, it needs to be SMIME compatible. So what do? Well, I take my email message, I hash its content, I run a hashing function over its content, I get a hash, and then I encrypt that hash with my private key. Remember, I have a digital certificate. That digital certificate is basically just a wrapper, just a container for my public key, which means that the private key is safely stored somewhere in my own computer. All right, I take my private key and I use it to encrypt the hash that is generated from my original email message. All right, then I take the contents of my email and I encrypt that content of my email with your public key. Now, I need your public key as well, so you're going to need a digital certificate as well. And I'm going to be using your public key because, well, you guessed it. Whenever you receive that message from me, the only one who can decrypt it is going to be the owner of the private key, and that's you. All right? Then I send my message to you in a blank email with an SMIME attachment. So my email basically becomes an empty email with an encrypted attachment. It's your job now to decrypt that and validate that encrypted attachment. So what do you do when you receive the email? Well, you decrypt the message with your private key because it was previously encrypted with your public key. right? And you're the only owner of the private key. And then you need to validate my digital signature, right? Remember, I hashed the content of my original message and then I encrypted it with my private key. That is a digital signature. So you need to validate that digital signature by decrypting it with my public key, which is freely available, right? Which is part of my publicly available digital certificate. Once you do this, you can validate the origin of that email message. You can be sure that it came from me, from Andrew, and you can also decrypt the content of the email, making sure that nobody else has saw the contents of that email apart from you. And that's how MIME works. As I said, it's a combination of encryption and digital signatures, which by definition is no easy task. But I think this is the easiest explanation possible for what actually happens in the background. Finally, one last type of application protocols worth mentioning and worth protecting are the protocols that deal with real-time communication, that is audio and video. Well, real-time communication in general uses two protocols. Those are SIP, Session Initiation Protocol. Remember that it works on TCP port 5060, right? And also a data channel. That is a separate connection just for transferring the real-time audio and or video data. So you have a separate channel for monitoring the connection, for initiating it, for tearing it down, for gathering statistics, for managing participants and everything else that happens on the side. Then we have a separate channel just for the data transfer. That's why we have two protocols in here. Now we also might have quality of service implemented in here, but this is not exactly a security feature or a specific protocol. If you want to know more about quality of service, check our previous videos. We did talk about them a while ago in quite some detail. So the security here is implemented kind of similar to HTTP. That is, we're running SIP over TLS. So that's going to be SIP over port 5061. Kind of easy to remember. Just add 1 to the clear text version. And also we can protect the actual data stream, the audio video data stream, by implementing SRTP, Secure Real-Time Transport Protocol. And the payload is being encrypted by using a key that is generated in the control channel, as you can probably expect, right? So SIP, in our case, SIP S, SIP over TLS, is going to take care of generating encryption keys for the data channel as well. Right, so we had a lot of application protocols to secure in this video. Thanks for watching. I hope you found this informative. You know what to do. Like, subscribe, support the channel, do whatever you want. Just make sure you watch the next video as well. Thank you. Bye-bye.